Okay, so what I'm going to do now is, in this video, go through task 4 of the definitions homework. So I'm in school again today, and I'm seeing some of you lots. You'll be popping in and out, so this video might have to be paused a few times. I've been asking a few people questions about their definitions, and generally people are doing really well. However, there are a few misconceptions. So listen carefully on this video, work your way through it. Try and listen to what I'm saying very closely, and listen to the way that I'm working these things out. Okay, so this is an exercise in reading equations and seeing what they're actually saying. Alright, and then trying to decide what definition best fits what you see. Okay, so if I look at this equation here, I'm reading this as 1 mole of calcium atoms. 1 mole of gaseous calcium atoms. That's 1 mole of gaseous calcium atoms. And they're becoming 1 mole of gaseous calcium 1+ ions and a mole of electrons. So it looks like I've got gaseous calcium atoms losing electrons to form 1+. That sounds to me very much like ionization. This looks, everything's in the gaseous state. This is the first ionization energy for calcium. And I might put the gas there, but it's first ionization for calcium. If I have a look at the definition below here, where I've got the enthalpy change when 1 mole of gaseous atoms, loses 1 electron per atom to produce gaseous 1+ ions. 1 mole of gaseous atoms produces 1 mole of, so it loses 1 electron per atom to form 1 mole of gaseous ions. Yeah, that's fine. Alright. So what's going on here then? This is 1 mole of gaseous atoms, sulfur atoms. I know they're atoms because there's no little numbers there. If it said S8, they would be sulfur molecules. But it's not. It's sulfur atoms, gaseous, gaining 2 electrons per mole. 2 moles of electrons. So 1 mole of sulfur gaining 2 moles of electrons to form S2-. Well, gaining of electrons is electron affinity. It's a type of electron affinity, but gaining 2 moles of electrons. So if you have a look at electron affinity, the first electron affinity is when 1 mole of gaseous atoms gains 1 electron per atom. That's this bit over here, gaining 1 electron. So if you're gaining 2 electrons, that looks to me like the first and the second electron affinity. So this one is a combination of sulfur gas gaining an electron to form sulfur minus gas, and then sulfur minus gas gaining another electron to become S2- gas. This is first and second electron affinity of sulfur. Alright? This equation does not match any of these on the sheet. It's a combination of the first and the second electron affinities. Alright, what's going on here then? So I know it's got a bit messy. So you've got 1 mole of aluminium oxide solid. And it's turning into gaseous aluminium ions and gaseous oxygen ions. So this to me looks like you've got a solid ionic lattice being dissociated into its gaseous ions, its constituent gaseous ions. This looks like the lattice enthalpy of dissociation for Al2O3 solid. That's an ionic solid. You can tell it's ionic because it's a metal and a non-metal. You can also tell it's ionic because it forms ions, which is a bit more of a clue really. So it's when you've got a lattice and it's broken apart into its constituent gaseous ions. Alright? That's the lattice enthalpy dissociation. It's this one, down at the bottom. Enthalpy change when 1 mole of a solid ionic compound is broken up into its constituent ions in the gas phase. Or constituent gaseous ions, as I prefer to say. Right, this is 1 mole of solid ionic compound forming aqueous ions. Now normally, I know this one, we would normally put plus AQ, but it's not written on there. This looks like you've got a solid substance and you've chucked it into water and it's become Na plus aqueous and Br minus aqueous. I'll draw what this one looks like. You've got NaBr, they're not meant to be overlapping, sorry, it's not covalent. NaBr, Na plus Br minus, Na plus Br minus, solid. It then turns into Na plus aqueous and Br minus aqueous. There you go, well aqueous means in water, so you've got Na plus aqueous and Br minus aqueous, Na plus aqueous and Br minus aqueous. That's what that's suggesting. NaBr solid, Na plus aqueous, which will be that, and Br minus aqueous. This is dissolving. Alright, well which one of them is that? Which definition is that? Well that's got to be enthalpy of solution, because that's to do with dissolving. And the enthalpy change when 1 mole of an ionic solid, let's have a look, 1 mole of an ionic solid dissolves in an amount of water large enough so the dissolved ions are well separated. Well, it's when a solid becomes aqueous ions. This is the lattice enthalpy of solution. Sorry about my writing here. For NaBr solid. This plus aqueous is optional. You can put it in, you don't have to put it in, and they haven't in this case. Alright, what have we got here? 1 mole of iodine in its standard state, forming 2 iodine atoms. I'm going to draw this. You've got iodine, it looks like that, I2, solid, becoming an I and an I. Well, it looks firstly like you're just breaking a bond. But it's not bond enthalpy, because bond enthalpy, this would have to be iodine gas. Alright? So it's not that. You're making 2 moles of iodine atoms. So you could think of it as an atomization. But atomization would be making 1 iodine from half an I2 solid. This equation to me looks like 2 times the delta H atomization of iodine, because you're making 2 moles of iodine atoms from the elements in its standard state. And atomization is where you make 1 mole. Okay, I'll leave it there. Okay, so that's actually quite a difficult one. So I'm going to just talk through this one again. Alright, so question 5. So iodine is I2. That's iodine solid is the standard state of iodine. So there are 2 definitions here that this looks like it could be. If you wanted to do the atomization, whoa, come on, focus. The atomization of iodine would be this. When 1 mole of iodine atoms in the gaseous state was made from the element in its standard state. This equation represents atomization of iodine. There is another equation that represents bond enthalpy, which is if you take gaseous iodine and you break it apart into gaseous atoms. This equation is delta H, I'll put this as bond enthalpy or something like that, Be. Here are 2 equations that you can find on your definition sheet. This is atomization, this is bond enthalpy. The equation you were given on question 5 looked like this. Iodine solid into 2I gas. Now, I hope you can see that this equation from question 5, it looks very similar to the bottom one, but the state symbols are different in the iodine at the start. And it also looks very similar to this one, but it's atomization but everything doubled up. Okay? So to me, the best way of describing this would be to say that this equation that you've been given, because the state symbols match, it effectively is 2 lots of atomization. If you double the atomization equation, so that would get rid of this, because a half times 2 is 1, and put a 2 in front of that, you would end up with the same equation here. So that is 2 atomizations. Okay? There is another way of looking at it, which is you could take the iodine and vaporize it and then do a bond enthalpy, but that's maybe complicating things. Okay, next. C3H8, that's propane, lots of oxygen, everything in the standard states, making carbon dioxide and water. This is combustion. Delta H of combustion of C3H8. That's easy. That's just burning. It's complete combustion. Solid aluminium, that's aluminium in its standard state, plus 3 oxygens, making 2 aluminium oxides. Interesting. These are elements in their standard states. That's a solid compound, but you're making 2 moles. This looks like the formation of aluminium oxide from the elements in its standard states, but you're making 2 moles. This is 2 times delta H formation for aluminium oxide, because you're making 2 moles. I can tell it's a formation because you're forming this stuff from the elements in their standard states. The only one on the definition sheet that comes close to that is enthalpy of formation, but because you're making 2 moles, it's 2 times enthalpy of formation. What that means is, if the enthalpy of formation was whatever, plus 612, this value would be plus 1,220, can I do maths? 1,224, it would be double. So, anyway, whatever, that's what that means. Alright, you've got gaseous ions, positive and negative, coming together to form a solid lattice. The enthalpy change when 1 mole of solid ionic compound is formed from its constituent gaseous ions, delta H bond lattice formation for calcium oxide. That's calcium oxide lattice being formed from calcium ions and oxide ions. Let me just represent that for you. Calcium ions, 2 plus, gas, so they're whizzing around. Oxide ions, 2 minus, gas, they're whizzing around. Coming together to form calcium oxide. Again, they're not meant to be overlapping. 2 plus, 2 minus, 2 plus, 2 minus, 2 plus. You're forming a lattice. If you're forming a lattice, it's lattice formation. Right, that's what that represents. Solid sodium forming gaseous sodium. 1 mole of gaseous atoms being produced from the elements in its standard state. That's delta H atomization for sodium. P4 to 4P. Right, what's going on here then? That is an element in its standard state, phosphorus. This is 4 moles of gaseous atoms. 4 moles of gaseous atoms. That looks like 4 times the delta H atomization of P4. Because you're making 4 moles of gaseous atoms. That's 4 times atomization energy. Atomization makes 1 mole of atoms. If you're making 4 moles of atoms, it's 4 times the atomization. Maybe that's the simplest way to say it. If you go back up to this one, question 5, if you're making 2 moles of gaseous atoms, so it's 2 times the atomization energy. If you're making 4 moles of gaseous atoms, it's 4 times the atomization energy. Right, HCl gas, hydrogen chloride gas, that's hydrogen chloride in its standard state. H gas and Cl gas. Now they look weird, don't they? It's not H2, it's not Cl2, it's not H plus, it's not Cl minus. So it's nothing to do with ions. So it's nothing to do with lattices. It's nothing to do with elements in their standard states, because these aren't elements in their standard states. This must be, everything in the gas phase is a clue here. This looks like a bond enthalpy. This looks like you're taking HCl, you're snapping that bond, and you're forming a hydrogen atom and a chlorine atom. This is delta H bond enthalpy for HCl. The enthalpy change when 1 mole of HCl bonds is broken in everything in the gaseous state. H2O liquid, forming two H's and an O. Alright. H2O liquid. H2O liquid forming two H's, so that's an H, an H and an O. Alright, let's think about this. And these are all gases, gas, gas, gas. Right. I'm just finishing this. We've got somebody who's walked in. I'm trying to work out this answer. Take a seat there. Put it in that way. Right, H2O liquid. So we're breaking bonds. If we've got individual atoms over this side, we're breaking bonds. Right, it's not just a straightforward bond enthalpy, because that would be H2O gas forming two H's and an O. So it looks a bit like a bond enthalpy. We're breaking bonds. To get from H2O liquid to these separate atoms, you must have had to go H2O liquid, then H2O gas, then H, H and O. This one's quite complicated, I suppose. And it is a combination of, if you think about maybe drawing a Hess cycle for it, to get from this side to this side, you could go to H2O gas, and then there. What would you call a liquid going to gas? That's vaporization, and then bond enthalpy. I think you'll find in the answers here, it's quite a tricky one. This equation can be represented by saying it's delta H vaporization of H2O, and the delta H, 2 times the bond enthalpy for OH. Let's put a big box around that. I'll have to come back to that one another time. But that's the answer, I think. Vaporize your water to turn it into gas, and then break two OH bonds. There might be a simpler answer to that. I got a bit distracted by this student, I'm not going to name people, walking in. Right, nearly there. Not nearly there. Pause video. Okay, so I'm starting again after a brief pause there. So, question 12. The point about question 12 is it doesn't really fit any of the definitions that you've done. It's a combination of definitions. It looks like a bond enthalpy, but the fact that the water is liquid means that you have to think about turning the liquid water into gaseous water first and then breaking the bonds. So it's a combination of vaporization of water and then 2 times the bond enthalpy. Hey, do you want to go and sit over there? Got another one coming in. I'm nearly there. I'm going to plough to the end of this. Right, question 13. Question 13 looks like 1 mole of gaseous atoms forming aluminium 3 plus and 3 electrons. So it looks like these gaseous atoms have each lost 3 electrons. Now that is an ionization energy, but it's a combination of the first, the second, and the third ionization energies. So delta H ionization energy for aluminium. Next one, you've got gaseous calcium 2 pluses forming aqueous calcium 2 pluses. I think that's quite straightforward. Normally we write plus AQ there, but that's delta H hydration for calcium 2 plus. On the sheet, it's there. You'll notice on the sheet that it has plus AQ, but you don't need to put that in. Last 2. I'm making this person wait. He doesn't mind. Right, oh my word, what's going on here? Question 15. On first glance, it looks like just straightforward ionization. Ionization of magnesium would be Mg gas, forming Mg plus an electron. So it's that sort of form. 2 plus and 2 electrons. So it looks like first and second ionization energy. But you're also dealing with this Mg solid. This is a combination of, what's this? Mg solid to Mg gas. Mg solid to Mg gas first. You'd have to do that first, which is atomization. Delta H atomization. And then the first and the second delta H ionization. So to get from Mg solid to Mg2 plus gas and 2 electrons, you would have to atomize the magnesium and then remove 2 electrons. So that's the answer there. The final one is magnesium in its standard state, oxygen in its standard state, forming magnesium oxide. That is just the enthalpy of formation of magnesium oxide. I hope that was useful. I've been a little bit distracted by various things, like my job, and I maybe haven't explained some of them well. This task 4 is much harder than you will be asked ever in an A-level exam. But if you are understanding me talking these through, that hopefully will make you better at the definitions. So next week we're moving on to using these definitions, which will hopefully make everything a lot clearer, because at the minute you're not quite sure why you're doing this. And as soon as we start using them in context, it'll get a lot easier. All right, done.